Hi everyone and welcome to a new video about BJT amplifier circuits. This is our example number 7. In this example we will look at the common-base amplifier configuration, which is very useful where the input is a current. So you can have a matched input resistor or impedance if you have a current input for your amplifier. That is very important for specific applications like the antenna circuits. Of course, we will work out in our example the calculation step by step and also verify these in our SPICE simulations. So let's look at our example. We have this circuit here given. Why is it called the common base? Because the base is here connected to the capacitor, and which is then connected to ground, so it is AC ground for AC operations. And we see it is the input which is also capacitively coupled, and this VI and RS is the model of our source, is connected to the emitter, and the output is again at the collector like in a common emitting amplifier, but also AC coupled through the capacitor C2. We have again 4 resistor configuration for the bias stability, R1, R2, RC and RE. We also have one DC voltage source, VCC, and the values are shown here for all these resistors. We also have the load, which is 6 kilo ohms here, and we assume for the transistor the base to emitter voltage is 0.7 constant. Now for this example we would like to calculate the voltage gain, which is VO over VI, where the beta is 100, and we repeat the process as we did in the previous examples for beta is 200 and 300. That's for the question A, B and C. But in question D, that is another example or problem where we repeat problem A, but then we will sweep the value of RS, which is this source resistor, which is the output resistor of this VI, which is our input voltage. And we will see what kind of effect it has in the gain. That is very important to see. Okay, let's move on with our example. We will assume, as always, that the transistor is operating in the linear region. That means the collector current is linear related to the base current using the beta. Okay, so we have now beta as 100 and then move on 200, 300. So this is a constant value. So the solutions, we start with the DC analysis and then we will do the AC analysis. For DC analysis, we consider the capacitor all open. So this is opened. The load is disconnected and also the source is completely disconnected. So we only have the 4 resistors, the transistor and the VCC. That's shown here. You also see the DC quantities in the circuit. First, we need to transform this to the Thevenin equivalent circuit as shown here. So the node B here, which is also there, which is the base node. We see now new parameters, which is the Thevenin voltage and Thevenin resistance, which is connected here instead of these 2 resistors. And we calculate the Thevenin equivalent circuit at node B for the Thevenin resistance using this. So the R1 and R2 will be parallel. The values are shown here, so we will use these values and you will get to 28.8 kilo ohms. Now in the same similar way as we did in the previous example, we calculate also the voltage at node B using the Thevenin equivalent circuit. That is the voltage division R2 over R1 plus R2 times VCC. Now if you do the calculations here, you will get 5.4 volts. So this is now what we can use, these 2 values in this circuit to move on, because if you work out the example here using this circuit, you might make a mistake by assuming that this input is an open, so you will by mistake probably think that the base voltage here is just a voltage division, but that's not the case. You need to use the voltage division here like in a Thevenin equivalent circuit. Okay, moving on to the Kirchhoff's voltage law at the input loop. So we make a loop here and that will be then V Thevenin is equal to R Thevenin times IB. So I will apply the Ohm's law directly for this resistor, plus the VBE, plus the voltage across RE, again using the Ohm's law. But we know the emitter current is given by beta plus 1 times IB. So emitter current is the IC plus IB, and since IC is beta plus beta times IB, we can say these 2 together will be beta plus 1 times IB. Now if I now substitute the emitter current in here, you will get the following expression where you see only IB. So if I now collect the IB terms together, I have this one, and I can now express IB in the rest of the parameters. And this is an important expression for the base current, and we will use it for the future calculations. So we start first with the current gain of 100. So let's continue. This is now the result, the Thevenin voltage, Thevenin resistance, and also the base current expression. So we start with a beta of 100 as said, and now we have here the IB. We just substitute the 100 here, that will be then 101. The RE is 1000, and we just also use the 5.4 for the Thevenin voltage and also the 28,800 for the Thevenin resistance, and the VBE, which is 0.7. So if you do the calculations here, you will get 36.21 microamps. In a similar way then, we can calculate now the collector current, which is then beta times IB, just 100 times this value. You will get 3.621 milliamps. And the emitter current will be then just 101 times the same base current, will be then a little bit larger than the collector, which is then 3.657 milliamps. So we have now everything. Let's also look at the output node, which is this VCE. So the VCC is then RC times IC, again the Ohm's law plus the VCE plus the volts across RE, which is then RE times IE. So let's substitute now the values here and express before that the VCE in terms of the parameters here. And you will get, if you do the calculations here, 4.101 volts. Just using the IC we have calculated, and also the IE, and also the resistors and the VCC. Okay, let's take this together. These are the DC currents, IB, IC, and IE. And this is the model we will use for our AC analysis. This is the AC model. This part here is the small signal model of the BJT. You can see the R pi from going to base to emitter. This is a dynamic resistor. You see the collector emitter connection here, which is a dependent current source, which is beta times IB or GM times V pi, which is the same and depends on what you want to use for your calculations. You see the capacitors are all perfectly shorted. So the base node, you see that is perfectly shorted. And since this is a ground for R1, and also this is a ground, so the R1 is effectively shorted. For R2. For R1 is a different story because the AC ground, VCC, is here, and the capacitor C3 is grounded. So that means the both sides of R1 is also grounded, so it's also gone. So you also short out the R1 there. So there is no R1, there is no R2 in the AC model. Here from the collector node, this is the collector node, you can see that REC going to the VCC, that is AC ground, and the capacitor is perfectly short, that is also going to the load and also the ground. So RL and RC are effectively parallel. That's why we have this parallel combination of collector, resistance, and the load. The input voltage is connected through RS. C1 is perfectly shorted to the emitter node, and from there we have an emitter resistance going to ground, that is also shown here, and that connection is now also going to the emitter. So this is the complete small signal model. Okay, we can now define the following: this current II, which is I in, and also IRE, which is this current. Because we need to set up the equation for the voltage gain, we don't have it yet. So first we start by defining the currents here, and we move on with our analysis. So we apply now the Kirchhoff's current law, which is KCL at node E. Now what do we see? We see the IB and IC are coming in, and also II is coming in, but IRE is leaving. So you can say IB plus IC plus I in is equal to this current through RE. But we know IB is V pi over R pi. That's just Ohm's law again. And we also know that IC is GM times VP or beta times IB. And we also know that this input current is this voltage minus the voltage at node E divided by the RS. But since this is V pi here, which is actually VI, minus, because you see the minus here, that's why we have this expression over RS. And if you do the minus reduction, you get the plus here. So this is the expression for the II. And you have also the current through the resistor RE, which is actually the reverse of the V pi, which is the minus of the V pi, because this node this node E is the minus of the V pi. That's why we have V pi over RE. Now we have now the expressions, and also using Ohm's law for this current equation using Kirchhoff's current law. So we can substitute everything here. That's shown here. So you recognize the following, and now we can simplify this. That's one of the options, by multiplying out the fractions. So you can multiply the left and the right hand side of this equation such that you don't have any fractions anymore. Now one of the options is just start, for example, with R pi, so left side multiply by R pi completely, and also the right side, and then also with RS, because I also need to get rid of this one, and also RE. But you can also do at once by doing R pi times RS times RE for the left side and the right hand side. That's actually what I do. And then you get this. So since this is multiplied with the first term by R pi times RS times RE, you only have this. So only R pi is not there. This will be multiplied by the three resistors. That's shown here. R pi, RE, RS. This is multiplied also by the three resistors, but I will of course lose the RS, so that's actually shown here. And this also multiplied by the three resistors, but I have now this one because I don't have the RE. Now we can now work out the parentheses here, so let's do that. And also bring this minus to the left side. First that actually, I mean. So first we bring this minus to the left side and then work out the parentheses here. So we work out the VI times RE, R pi, and then plus V pi times RE, R pi. Now let's now collect the terms for V pi together, because we'll have all the V pi terms here. This one, this one, this one, and all this one. So we have four terms. These are all here, and we have only one VI term here, which is here. We can also make a simplification. I mean, some equivalency here in this parentheses, because you see the RE, RS here. That's also shown here, and we can do 1 plus the GM times R pi times this multiplication. You can also see the R pi here together, so we can also take it out and also do RE plus RS. That's shown here. Now we can bring again the VI term to the right side, and then we can express VI is equal to this complete term in the left side divided by the minus RE, R pi, or you place the minus sign in the numerator. And this is the expression for the input. You can see it's quite complicated, but we will see that it is useful later for our voltage gain expression. Okay. Let's call this equation number 1. Well, what is now the expression for the VO? That is a lot simpler, because the VO is here. That's the voltage where we measure the output. And the current flowing through the resistor here, RC and RL, multiplied by this resistor will be then VO. But that current is just this IC, but in the reverse direction, which is then a minus IC. So we can say it is minus IC times the parallel combination, or minus GMV pi times this parallel combination, which is shown here. And let's call this now equation number 2. Okay, let's bring it together. And also the values here, because we need them shortly. So VO and VI, and we can now place them on top of each other for the voltage gain. So then the voltage gain will be given by this expression, and then everything is in here. You see the VO in the numerator, and this is VI in the denominator, which is just what we have calculated for the equation number 1. You see the V pi can be divided out, and we can also place the RE and R pi in the numerator. So you will have this expression, and you will also lose the minus. So it is actually a non-inverting amplification here, and not an inverting amplification like we had in the common emitter amplifier. Okay, now this is the expression for the voltage gain. We also have the RC and RL, that is this expression. And we can calculate now using the 2000 for the RC and the 6000 for the load, and that is just 1.5 kilo ohms or 1500 ohms. We also need the GM and also the R pi values here. So that's also one of the parameters we need to calculate. GM is IC over VT. That is then this value. You will get 0.1393 Siemens. The R pi is given by this expression. Again, the DC quantities for the currents. So if you do the calculations here, you will get 718 ohms. Now, let's then substitute all the values in here. If you do the math for yourself, it will be a 3.908, and you see it is positive, and it has some amplification. It is not that much. You can, of course, influence the value of here. You can increase that, but it is a plus, so non-inverting amplification. This is for 100, beta of 100. Moving on and looking at the simulation results, and then for the DC analysis, we have this. So we collect all the DC values. You see here the circuit, and we see the base current is very close to what we have calculated, the collector current, emitter current, and also the collector emitter voltage. So they are really close. There are small errors. That is indeed the case. That's due to the model of the BJT, which is more accurate than the model we will use. So that's why we see small errors. So in the, for example, the collector to emitter voltage, we see approximately 54 or 55 millivolts off. That is not that much, actually. Okay. Moving on to the transient response in the simulation results, and we had this voltage gain. The blue one is our input. The red is output. You can see it is non-inverted, so it is in phase. The input is given by 10 millivolts peak sine wave, pure sine wave at 10 kilohertz frequency. So peak is 20 millivolts. The output peak voltage is calculated just looking at the output maximum and the minimum values. And if you do the calculation, you will get 58.08 millivolts there. And if you now just calculate from these two plots the voltage gain, you will get 2.904. And we had 2.908 from the calculation. So very close to what we have calculated. So the verification is indeed made here from the simulations. Now, we now move the current gain of beta for 200. So we'll increase that by a factor of 2. And again, the same circuit doesn't change, only changes the beta here in this expression. So this is a very important equation. So the beta is changed, IB is changing, so I go a little bit faster. IC is changing again in the same format, and IE also. And also the VCE will change, and that will give now a new value. Okay, let's bring it together. And this is again the AC model for this circuit. We know what we have this. Now we can also calculate directly the new GM because the IC has changed. Because that is now this one, it will be now a new GM value. And also the R pi will change because the IB has changed and that is increased now. That is now 1271 ohms. Now using the voltage gain, we have the expression here. We can calculate a new value which is now 2.929 as the voltage gain, which is not that much compared, the difference is not that much compared to the value we had for beta as 100. Okay, so moving on with the DC analysis for the simulation result, this is the circuit, and now the change here is that the beta is 200. You can see the base current is 20.54 approximately, so very close to what we have. The collector current, the emitter current, also the collector emitter voltages. So you can see they are very close to what we have calculated. There are of course small errors again due to the parameters in the BJT. Okay, now the transient response, we had this voltage gain. This is the blue line, which is our input, and this is our output. And again, in phase, the same voltage, peak 20 millivolts, 10 kilohertz. You see the peak value for the output. And if I now just calculate the peak output divided by the peak input, I will get 2.925 as the gain, and we had calculated 2.929. So a very small difference actually between the simulations and the calculation. So again, verified. So next one is the beta of 300. Let's move on. So again, the DC circuit here, and we make only the change of beta of 300. So we can speed up the process again. The beta is 300. You get a new base current, new collector current, new emitter current, and also the new VCE. That's also shown here. So moving on and then looking at the small signal model, but then again using the voltage gain expression, but for that we need a new GM and also the new R pi. So GM is this one, new GM using a new collector current, and also the new R pi using a new base current. So that's what we have. So these two values will change in our expression for the voltage gain, which is shown here. So if we substitute the values here, you will get 2.937. So that's the new value using the beta 300. Okay, looking at the DC analysis result in the simulations, this is the circuit. You see the base current is 14.3 approximately. Also we have approximately collector current, collector emitter voltage. It's also very close to what we have calculated. Again, small errors due to the parameters in the BJT model. looking at the simulation results for the transient response with this voltage gain we have calculated. The blue one is again the input and the red is the output. This is the voltage for the input. It's 20 volts, peak pure sine wave, 10 kilohertz. And this is the peak peak value for the output voltage. Again, similar calculations, and you can see that the gain now is 2.932, but we had calculated 2.937. So again, very small difference between the calculations and the simulations. So again, verified. So now we will see the effect of the source resistor sweep. That's actually the question D. We keep the beta as 100. Now we will sweep the value of the RS. So we start with 0 and then move on to 5000 in steps. Now we have these values. So these are still the same for GM and R pi, for specifically the 100 for beta. And this is again the parallel combination of RS, RC and RL. Now the voltage gain expression was given by this. Now, if you do, for example, the following here, for extreme cases, if you make the RS exactly 0, that means this part goes away, first part in the denominator. And you also lose this one, so you will get the GM times RE times R pi and times the parallel combination of the RC and RL divided by R pi and RE. But these two products is also here. So you will lose that and you will get actually this expression, which is the maximum possible gain. If you calculate that, it will be 209 approximately, and this is really the maximum possible voltage gain. That means, as said in the beginning, this is really for the current injection circuits, where we have a very small source resistor and also very small input impedance for the circuit. But if the RS is going to infinite, so very large, and logically you can see that then this value here will be then very large, and then the AV goes to 0, and that's the minimum voltage gain. So we go from 209 all the way to 0. Okay, now we have several values here, so instead of calculating everything step by step, you can also look at a table which gives you more insight and information. RS is 0, this is the maximum voltage gain. If you go to 50, it will go down drastically. If you go to 100, so you can see the values here. And if you go to 500, which is what we had calculated, and if you go to 1000, it will be 1.464. But if you go a little bit higher, to 2000, it is not amplifying anymore, but is actually attenuating. So for 5000, or even for larger values, you will actually not amplify, but attenuate. Still, of course, non-inverted, but it's a difference between amplification from this part to that part. Okay, let's also look at the impedance matching at the input. That is also one of the important things, because the voltage gain was given by this one expression, and the input impedance can be determined from the small signal model. Now the input impedance looking here is Z in, and that is actually the input impedance looking up and looking down in parallel format. So you can see ZIE, so the emitter in the emitter direction, also in the emitter resistor direction. So the parallel combination of the ZIE and RE. What is ZIE? Now ZIE is the parallel combination of this R pi and the GM as the conductance, which is of course 1 over GM, which will then be resistance. What is GM? Now specifically it depends on the beta and also other parameters. So every circuit configuration will have a new GM and also R pi. You can calculate this or express this parallel combination using this. So it will be then 1 over GM plus the 1 over R pi, and then that also 1 over the complete quantity. And you can now also write it down like this, and you can divide the numerator and denominator by, or you can express, by the way, GM and R pi times beta. That's actually what I want to say. And you see 1 plus beta is very close to beta if the beta is 100, 200, 300, really large values. So it is approximately this one. But this is 1 over GM. So you can sort of remember or assume that looking into the emitter node of the common base amplifier, that the input impedance is close to this 1 over GM for going in the emitter node. Of course, you have the emitter resistance, so that will be then parallel. So together, Z in will be then 1 over GM in parallel with the RE. Do we know the 1 over GM? That is again dependent on the beta and the circuit parameters. We can also write down this in this format. And if I now use the values specifically for 100, will be then 1000 over 1 plus. This was for the 100. We have calculated that. The GM value 0.1393. And if you now calculate this, it will be then 7.13 ohms. And that impedance, input impedance, is the characteristic impedance for this specific circuit. So if you want to have a maximum power transfer from the input to this node, you need to make your RS also 7.13 ohms. That is what we see here. So if the source resistance is equal to the input impedance, then we have matched impedances at the input. So for RS is equal to Z in, which is the input impedance. The voltage gain will be then 104, which is the half of the maximum voltage gain actually. So the maximum voltage gain was this one. So this is due to rounding off. We see that is half of this one, so it is 208 or 209 approximately. Divided by 2, you get 104 or 104 point something. And that is really the half of this gain. But you get then the maximum power transfer. So you lower your gain, voltage gain, but you get the maximum power transfer. Okay, now let's summarize now the results. We have now the calculations here, the summary. We have the beta is 100, 200, 300. You see the base currents, the collector currents, and emitter currents, and also the collector emitter voltages. But the important thing is the voltage gain. The voltage gain is approximately 2.91 in both cases, in all cases. So it is 2.9 here, 2.93, 2.94. It's not changing that much. We see the beta is changing drastically, so 3 times larger, but this is just changing maybe 3, 4, 5%. So it's not that much a change. So it's quite stable in terms of the voltage gain. Now looking at the simulation results in a summary, this is the DC values for the beta is 100, 200, and 300. You see how the base current is changing, how the collector emitter voltage is changing, etc. In a similar form, we can look at the simulation results for the transient. Again, the plots, beta is 100, 200, and 300. These were the calculated values, and we had here the determination of the voltage gain from the simulation. You see they are very close to what we have calculated here. So we can say this is indeed a very nice result for this common-base amplifier. Again, the common-base amplifier is specifically useful when you have a current as your input. So if you want to amplify a current, then this common-base amplifier is very suitable. In a similar form, you can do that with a MOSFET where you have a common gate amplification. And we will discuss this also in another video on this channel. Alright guys, this is for our example about the common-base amplifier using an NPN BJT. And we have discussed the DC analysis again and also the AC analysis, and we'll have discussed the effect of the beta and also the effect of the source resistor and looked at the characteristic impedance for this specific circuit. If you have any questions, comments about this example, please let me know. I will try to answer them as soon as possible. See you next time in another video. Take care.